Hello everyone, welcome to the series of lectures on the course Foundations of Mathematics. This is part 3 of the third chapter, Functions, and in this lecture I will talk about one-one functions, also called as injective functions. So let's see what are one-one functions. If I have a function f from the set x to the set y, then this function f is said to be 1-1 or sometimes 1-1 or sometimes injective if for each pair of points x1, x2 in the domain which are not equal, their corresponding images f of x1 and f of x2 are not equal. Okay, so whenever you pick up two different points in the domain, their images in the codomain should be different. If this happens for every pair of points in the set x, that is the domain of the function, then we say that the function f from x to y is a 1-1 function. So geometrically looking at this, supposing I have some set x here, that is the domain, and this is my function, and let's see this is my set y. Then supposing I pick up two different points here, let me call this as x1 and let me call this as x2, such that x1 is not equal to x2. Then their images here will be different. All right, they should have different images. So different points in the domain should have different images in the codomain. If this happens for each and every pair of points in the set x, then we say that the function is 1-1. Okay, so a function which is not 1-1, how will it look? Let me draw one function. Let's say this is a set x and I have a function. Let me pick up g now from x to y. Let's say this is y. When will I say that a function is not 1-1? That will happen if you are able to find one pair of points x1 and x2 which are different, but they go to the same point that side. Okay, so if you are able to find two different points in the domain which are mapped to the same point in the codomain, then the function will not be 1-1. Okay, so graphically looking at it, it looks this way. So you will see two or more points from the domain going to the same point. Now if exactly 2 points are going to this point, then it is called many one function. Okay, or 2-1 function also sometimes. Now let me put down the definition of 1-1 function using quantifiers. So what it says, for every pair of points in the domain which are different, their corresponding images are also different, right? So what do I have using quantifiers? Using quantifiers, a function f from x to y is 1-1 if for every pair of points x1 comma x2 in x such that x1 is not equal to x2, their corresponding images should be different. That is, f of x1 is not equal to f of x2, right? For every pair of points x1 and x2 in x such that x1 is not equal to x2, their corresponding images, that is f of x1 and f of x2, must be different, right? So this is using quantifiers the definition of a 1-1 function. Another way to write this 1-1 function would be this. What you do is you form one set, let's call it A, and in A what I will do is I will collect all the ordered pairs x comma y in the Cartesian product of x cross y here, Cartesian product of x and y, such that x is not equal to y. Okay, such a set I'll pick up. I'll pick up all the ordered pairs of the form x comma y in x cross y whose first coordinate is not equal to the second coordinate. So I'm picking up points, ordered pairs whose coordinates are different. Then if I call this set as capital A, then I can rewrite this definition of 1 function as a function f from x to y is 1 if for every pair of points in the set capital A, if for every x1 comma x2 in the set capital A, or you can say let's use some other notation, for every pair of points let's say p comma q in A, f of p is not equal to f of q. Can you see? Does it mean the same? Now when I say for every point ordered pair p comma q inside A is consisting of all the ordered pairs whose first coordinate is not equal to the second coordinate. So whenever I pick up a point p comma q, this ordered pair in A, I'm already saying that p is from x, q is from y, and p is not equal to q, right? No, I've made a small error here. This y is actually x itself. That's not y. Okay, it's x cross x, not x cross y. I made a small error there, so I'll rectify that. Yeah. Okay, so x and y, both these uh, points are from x only, and I'm looking at the Cartesian product x cross x. Okay. Then for every point ordered pair p comma q in A, f of p is not equal to f of q. So when you say that p comma q is there in A, this means p comma q are both there in the set x, because p comma q is there in A, and A is a subset of x cross x. So both are there in x, and p is not equal to y. Right? So this condition is worded in a different way. So 1 function can be defined in this manner also. Right? Now moving on to the examples of 1 functions. Before this one, you can look at the identity function. Define function f from R to R by f of x is equal to x. Then if you pick up two different points in R now, supposing p comma q are 2 points in R which are not equal, then because p is not equal to q, p is nothing but f of p and q is nothing but f of q, right? So if you pick up two different points p and q from R, then f of p is not equal to f of q, because p itself is f of p and q itself is f of q. So this function f is 1 identity function. So identity function is 1 right? I hope that's clear. Now moving on to the second example, if you look at this function f defined from open interval 0 comma 1 to R, defined by f of x equal to 1 by x. So 0 is not there in the domain, so 1 by x is well defined, right? So if I pick up 2 points x comma y in the domain, that's 0 1, such that x is not equal to y. Okay, such that x is not equal to y. This implies if x is not equal to y, then their reciprocals will be different. 1 by x will not be equal to 1 by y. So this means 1 by x is nothing but f of x, that is not equal to 1 by y, which is f of y. So if I pick up two different points in the domain of this function, then their images are different. and therefore we can conclude that this function f is a 1-1 function. Clear? What can you say about the constant function? If I give you a function, say define h from r to r by h of x is equal to, let's say, 10, then every point is mapped to 10 here, no matter which real number you take. This works for all r, right? So you can pick up any 2 points in the domain now of your choice. So if you take 2 and 3 in r, both these points are there in r, and 2 is not equal to 3, but they are different points, but the images, if you see, both are equal to 10, so their images are same. So different points are there in the domain which have same images, right? So this function, sorry, this is h and not f, this is h here. Okay, so let me correct that. So that is h of 2 is equal to h of 3 is equal to 10, right? So the function h is given to me, which is the constant function, is not 1 1. Clear? So this is an example of a function which is not 1 1. Next, look at this function. Consider the function f from r to r defined by f of x is equal to x cube. Is this function 1 1? We will show that this function x cube is 1 1. Okay, so we need to prove that this function is 1 1. So to show that it is 1 1, what I have to do? I have to take two different points in the domain, right? So let me start with 2 points a comma b in R such that a is not equal to b, right? So our claim will be to show that our claim is f of a is not equal to f of b. If we are able to show this, then we can say that the function x cube is a 1 1 function, right? Now, showing that f of a is not equal to f of b is same as showing that f of a minus f of b is not equal to 0. If they are not equal to 0, if their difference is non-zero, then they are not equal, right? So this is what we will show. Okay. In fact, further you can reduce this to, this is same as showing that f of a is a cube and f of b is b cube. A cube minus b cube is non-zero. This is what we have to show, right? And note that a is not equal to b. It's given that a is not equal to b, right? So since a is not equal to b, a minus b is non-zero. This is one conclusion from this fact, right? Now, I want to show that a cube minus b cube will never be, sorry, not empty, 0. Okay, I want to show that a cube minus b cube will never be equal to 0. So let's start with the expression for a cube minus b cube. You can factorize this as a minus b into a square plus ab plus b square, right? So when will a cube minus b cube be non-zero? Only when these two brackets are non-zero, right? If these two brackets are non-zero, then I can say that a cube minus b cube is not equal to 0. So this is what we have to look out for now. Now a and b are two numbers, so we will handle this case by case. Let's look at case 1. Supposing at least one of them is 0. At least one of a and b is 0. At least one is 0 meaning Let's assume that one of them is 0. So without loss of generality, I'll assume that A is not equal to 0. Let's assume that A is not equal to 0, right? Sorry, I have to assume that one of them is 0. So I'll assume that, I'll just erase this. I'll assume that A is equal to 0. Okay. Now, because A is 0 and we know that A is not equal to B, right? So A is 0. So this implies B is not equal to 0. This is since A is not equal to B. If B is also 0, then both of them will be equal, right? So B is non-zero in this case. So this implies since A is 0, A cube is equal to 0. And since B is not equal to 0, B cube will not be equal to 0. That means A cube is 0 and B cube is not equal to 0. That means they are not equal to each other, right? So A cube is not equal to B cube. That's what we wanted to show. A cube is not equal to B cube. Yeah, that is same as saying that f of A is not equal to f of B, right? So if one of them is 0, then f of A is not equal to f of B. So one case is done. Case 2 is when both of them are of same sign. A and B are of same sign. That means either both of them are positive or both of them are negative. Okay. Now, since A is not equal to B, we know that A minus B is never equal to 0. This is one thing. Also, A and B are of same signs now. So what you can say about A square plus AB plus B square? Now I am assuming that they are non-zero. They are of same sign. That means either both are positive or both are negative. Because if one of them is 0, that case is already done. Right? So if both are positive, then A square is positive, AB is positive, and B square is also positive. So their product will be positive. Right? If both are negative, then A square is positive, A and B are negative, both are negative. So their product will be positive again, and B square is always positive. So in either case, this is a positive number and this is also not equal to 0. That means their product A minus B into A square plus AB plus B square. This can never be 0 because one of them is non-zero, the other is positive. Right? So this means A cube minus B cube is not equal to 0, which means f of A is not equal to f of B. Right? So in the second case also we showed that f of A is not equal to f of B. Now one case that is left is they are of opposite signs. So case 3 is, you can say A is positive and B is negative. Okay. So because they are of opposite signs, A is positive and B is negative, this implies A cube will also be positive because cube of a positive number is positive, and B cube will be negative because cube of a negative number is negative. So one of them is positive, the other one is negative, so they are not equal to each other, right? That's clear. So this implies f of A is not equal to f of B again. So in all the cases we have shown that f of A is not equal to f of B. So if you pick up any two different real numbers, then their images are different. So this function f is 1 1. Okay, so x cube function is 1 1. Next we have this proposition which says a function f from x to y is 1 1 if and only if for every points x1 and x2, for every pair x1 and x2 in x, f of x1 is equal to f of x2 implies that x1 equal to x2. Can you all recollect something looking at this expression? what does the definition of 1 1 say? F is 1 1 means for every x1 and x2 in X which are different, if x1 and x2 are different, then their images are different, right? This is the definition of 1 1 function. Then what is the contrapositive of this? That means I will have to look at the negation of this part. So if f of x1 is equal to f of x2, then the negation of this, and that will be x1 equal to x2, and that's what I have here. So another way of looking at 1 1 function, the definition is this. For every points x1 and x2 in the domain, if f of x1 is equal to f of x2, then the points x1 and x2 have to be the same. And this is nothing but the contrapositive of the definition, right? So both the definition which I've stated now in the previous slide is equivalent to this statement. I can call this as, let's say, star is equivalent to this statement star. Okay, so you can also use this as the definition, and in many problems, you know, this second definition, the contrapositive of the definition, actually is useful. So let me look at that one example. Supposing I have a function f from R to R given by f of x is equal to 3x plus 2. I want to check whether this is 1 1 or not. Okay, so what I'll do, I will start with 2 points x and y in the domain such that f of x is equal to f of y. If I am able to show that x is equal to y, then the function is 1 1. So f of x is what? 3x plus 2. F of y is 3y plus 2. So you can cancel off 2. So this implies 3x is equal to 3y, which implies x is equal to y. So if f of x is equal to f of y, then x is equal to y, and therefore the function f is a 1 1 function, right? So we have used the previous proposition to show that this function is 1 1. Now the next question that arises is, if I have a function f from x to y, then when is the function f not 1 1? That means I want the negation of the definition of 1 1 function. So a function f from x to y will not be a 1 1 function if f is not 1 1, if you have to negate the definition. Okay, so the definition says for every point x1, x2 which are different here. So for every point x1 comma x2 in the domain, that is a set x here, the domain of the function, okay, such that x1 is not equal to x2, what should happen? Sorry, this is, I'm writing the definition of 1 1 function. F of x1 should be different from f of x2. This is the definition of 1 1 function. Now I want to negate this. So when will I say that f is not 1 1? F is not 1 1 if you have to negate this now. So there exists points x1 and x2 in X which are different, okay, but the images are same. So if you can produce 2 points in the domain x1 and x2 which are different but their images are same, okay, so somewhat like this, the images have to be the same, then we say that the function is not 1 1, right? And another way of saying this would be using the proposition f of x equal to f of x1 equal to f of x2. If you can find points x1 and x2 in the domain such that f of x1 equal to f of x2 implies x is not equal to y, then the function is, sorry, not y, that's x2, okay. then we say that the function is not 1 1, right? So here is an example of a function which is not 1 1. If you look at f from R to R defined by f of x equal to x square, can you find 2 points in R which are different but the images are same? You look at x equal to 4 and y equal to -4. X is not equal to y, right? 4 is not equal to -4. But what is f of x? That's 4 square and that's 16. And what is f of y? That is -4 the whole square and that is again 16. So f of x equal to f of y, right? And therefore the function f is not 1, right? So this way you can look out for more functions which are 1 1 and which are not 1 1, and you can see by drawing the graph how that appears. Okay. Now supposing I have a function, and let's say I have its graph with me. Let's say this is the graph of my function, some function, arbitrary function, and let's say the graph of that this function looks like this, and this keeps on moving. Okay. Now this is a function. Now if you pick up this horizontal line here, let me mark that in let's say red. If you pick up this horizontal line, it cuts the graph of the function at 2 points, right? Two distinct points. So suppose the horizontal line, let's call it y equal to alpha. So here is the point minus alpha. Okay, I'll call it alpha. It could be negative also. So here is the point alpha, and that is the line in red which I have drawn, y equal to alpha. So it cuts the graph at two distinct points, right? So let's say the x coordinate here where it cuts this point of the graph is x1, and where it cuts this one is x2. Okay, so it cuts the graph at two distinct points, and which are the points? x1 comma alpha and x2 comma alpha, right? So these two are distinct points, meaning what? x1 is not equal to x2 because their second coordinates are same. So if the first coordinates were also same, then these 2 points would have been same. But I am assuming that these two are distinct points. So this means x1 is not equal to x2, right? But what is the image of x1? That's alpha. Image of x2, that's alpha. But their images are same. So what can you conclude about such a function? That's not 1 1, right? So this is the graph of my function f from R to R. Okay, so what is the conclusion? If you have a function and there is a horizontal line which touches the graph at more than 1 points, okay, at more than 1 point, then the function is not 1 1. So for a function to be 1 1, what should happen? Every horizontal line you pick up, no matter which horizontal line you pick up here, that should cut the graph at most once. Okay, it's okay if it doesn't cut. This line doesn't cut, that's okay. But no matter which horizontal line you pick up this way, no matter where, how far, how close, anywhere you like, you draw a horizontal line that should not cut the graph at more than 1 point. Okay, so this is called the graphical test for checking whether a function is 1 1 or not. Okay, so function f from R to R is 1 1 if and only if every horizontal line intersects the graph of the function f at most once, maximum once. Okay, so it is possible that it doesn't intersect also, right? So if you see the function now, let's say the identity function, that's here, approximate diagram I'm drawing, more or less this. So that's a function, identity function. No matter which line you pick up, horizontal line, okay, so that is never going to cut the graph at more than 1 point. Okay, it is cutting exactly at 1 in this case. So such a function is said to be 1 1. Okay, so that's 1 1. But if you look at the function x squared, okay, this way and this way, there are so many horizontal lines anywhere you can draw above the x-axis, it will definitely cut the graph at 2 points. Okay, so this function is not 1 1 using the graphical test, right? But if you restrict your domain to only positive in this case and you only look at this half, then it will cut exactly once and then it will be 1 1. Okay, so everything depends on the domain, which points are there in your domain and which are not, right? So using graphs also, looking at the graph of a function, you can decide whether a function is 1 1 or not. Okay, so I will end this session here, and in the next session I will talk about onto functions or surjective functions. These are my references. Thank you.